now we're going to move to the next session, and this is the Lightning Talk session. As you can see, there's 2 tracks that are happening in parallel. If you want to attend the first track, the privacy and security track, please stay on this call. And Adria will be hosting this track. If you want to attend the optimization system and analytics track, please switch to the Google Meet that was just posted in the chat box.
The first speaker will be Zheng Zhu. Next slide. Yeah, speaking about, from Google, speaking about practical and private deep learning without sampling or shuffling. Go ahead, Zheng.
Thanks, Adria. This is a collaborative work with many of my Google colleagues. And we will talk about this method that does not rely on sampling or shuffling and can get us differential privacy in machine learning, and particularly application in federated learning. Next slide, please. Okay, let's start a little bit on how we commonly apply differential privacy in federated learning. What we often use is this method called DP Fed averaging method. If you're already familiar with federated averaging, like see every round, it starts from the server send a global model to clients, and the clients do some local updates. And each client will send their local updates to the server, and the server will use the aggregated updates to update the global model and start the next round. How to apply differential privacy in these federated averaging algorithms? You made 2 relatively simple changes. Before sending the client updates to the server, you will clip the updates to bound the sensitivity for differential privacy. And on the server side, you will add noise proportional to the sensitivity. And then you can get a differential privacy bound after that. Next slide, please. And to get a good utility privacy trade-off for this DP federated averaging method, essentially it's like applying DPSGD on the server side. We rely on some sampling for privacy amplification. And that assumes that a device will participate with a probability Q. Next slide, please. Okay, if you look at the figure on the right side, this shows the privacy utility trade-off for a Stack Overflow dataset in federated learning. The x-axis is the epsilon for privacy, and y-axis is the test accuracy. The 2 curves are DPSGD on the server side, which is DP Fed averaging in federated learning setting. One is without amplification, another is with amplification. This amplification is achieved by assuming sampling of uniform sampling. Then there's a big gap between the privacy utility trade-off. Next, please. And in practical federated learning, this is a uniform sampling is very hard to achieve in a real system. We have a large population which can be good for privacy, but the availability of these clients, and we have only limited control on the availability of these clients in each round. Particularly, whether a client will join training each round is often determined by a lot of local criteria. For example, a client will join only when the plug-in charger have a reliable Wi-Fi connection or other criteria. Next, please. And next, please. Let's go through all the animation here, maybe. Here, to tackle this difficulty on the sampling problem in practical federated learning system, we propose this method called DPFTRL. Remember, in DPSGD, in all the differential privacy methods, what you really need to private is this prefix sum of gradients, and you use them to update. Instead of adding like uncorrelated noise to each of the gradient, we use these tree aggregation protocols, which can add correlated noise to the prefix sums. Next, please. Next, please. And by using some Honecker tricks, we can further reduce the variance in this training process. Next, please. I will skip the theory results, but we can get the best theoretical guarantee for a single pass algorithm. Next, please. And if you look at the privacy utility trade-offs, if we use DPFTRL, it can outperforms amplified DPSGD by a large margin. And for epsilon is larger than 2, it can also outperform DPSGD with amplification. Next, please. If you look at the like non-private accuracy, when you don't apply differential privacy method, it's about 25. If you only increase the computation a little bit, you can significantly boost the performance, get you closer to the non-private accuracy. Next, please. Based on this, we often use this principle in practice by simultaneously increase the batch size or the report goal in practical federated learning setting at the noise multiplier. The utility won't change a lot. Next, please. And next, we verify this in practice and showing that this hypothesis hold in practical system. Next, please. Based on this hypothesis, we fix we assume that the utility won't change if we simultaneously increase report goal and the noise multiplier. And as you know, if you increase noise multiplier, you can get better privacy protections. This shows a privacy computation trade-off, where the x-axis is the user privacy epsilon, the y-axis is the report goal. Next, please. In practical system, if you look at the two blue curves with a report goal at about thousands, you can get an epsilon around 10. I will stop here and happy to answer some questions.
Thanks so much. Are there any questions? I'll ask a question myself. Could you comment on the threat model? Like, this is differentially private with respect to whom, and how do you achieve this correlation in the noise generation across rounds?
I'm asking about the simulation experiments or the privacy model?
The privacy model.
The privacy model, we are like I said, we are trying to protect the prefix sum of the gradients. And we achieve that by building a tree structure. And each node of the tree represents the part of the sum. The main idea is like in DPSGD, you assume that one gradient will affect all the prefix sum, but it's actually not. There are some independence there.
So, and Adria, to add to what Zheng said, the assumption here is that the server is trusted, and the server can also collect all these gradients and has memory if you want to store these gradients. So when you do this tree aggregation protocol, you need to store some states that have not been privatized.
Yeah, also comment on that is that that's the assumption on the theoretical side. In practice, we kind of immediately delete all this. We don't hold this in the system in practical implementation. But if you're curious about how we implement that, I will have another tutorial later, 2 days later for TFF, and we'll talk more about the implementation. That's nice.
Yeah. I see that Ali has a question. Nice to see you, Ali. But we're running a bit late, so if you could ask that offline, that'd be great. So let's move on to the
chat box. Yeah.
Or on the chat box, and then Zheng can reply, as we go. That sounds great. That sounds exciting. All right, so next talk will be by Albert. Nice to see you here, Albert, which will be about shuffle privacy, vector sums. Go ahead.
All right, so I'll be talking about the vector sums in the shuffle model of differential privacy. So next slide. So this is going to be a core piece of shuffle private stochastic convex optimization, joint work with Matthew Joseph, Junior Mao, and Binghui Peng. Next slide. So just to make sure we're all on the same page, the shuffler model is made up of these following pieces: a randomizer, a shuffler, and analyzer. Next slide. And so like the local model, we have the local randomizer where it applies randomization to user data, and we don't have trust in the analyzer. Next. But here we have the shuffler, which applies a uniformly random permutation to user messages. So the output is like a bag of messages. And now also notice that we're allowing multiple messages per user. So you have like 2 envelopes in the mailbox, let's say. Next. And so the view of the adversary is going to be the output of the shuffler. So we want to make sure that this output is differentially private. And so we're not so concerned with the privacy of the randomizer, so long as the composition of shuffle and randomization is private. Next. So what's the problem? The problem is that users have vectors in some L2 ball, and you want differential privacy. Meanwhile, the analyzer wants the estimate of the sum with low L2 error. And it's going to be a building block for stochastic convex optimization, like I mentioned before. And I should note this problem was also studied by Gerges et al. But one difference with our work is that their shuffle protocol is constrained, 1 short message per user, whereas we explore what's possible when we have we don't have this constraint. Next slide. Next. Is there a bug with the view? Okay, here. Yeah. So our solution is that we have a shuffle protocol with expected L2 error d over epsilon squared, and it's close. And this is close to the Gaussian mechanism in the central model. And fundamentally, it's basically parallel executions of a scalar sum protocol. And to keep track of the privacy budget, we use a generalization of advanced composition. And I should note that this is a general template. The scalar sum protocol can be changed to something else. So the improvements to communication complexity are possible. But we stick to a simple protocol for readability of our paper and this talk. Next. Next. Oh yeah, I have the tilde hides lock terms, just to, next. Yeah, so what is our scalar subroutine? So each user has a numerical value between 0 and 1. We convert to a fixed point representation of G bits. And then we also sample B bits from a Bernoulli. So now we have G plus B bits. I'm going to send them all to the shuffler. Okay, so why is this private? Well, the view is a bag of bits, and changing a user's value changes at most G of them. And so if the variance is large enough, it'll mask that change in a differentially private way. And one special property to note is that when the sensitivity is small, the privacy guarantees become stronger. Right? So if the change is very small, we're adding the same amount of noise, so it's more uncertain. The adversary is more uncertain. Next. Yeah, so we have composition. So we repeat this protocol multiple times in parallel for each coordinate. And so the expected L2 error is just the sum, so it's d over epsilon squared. But what's the privacy guarantee? Well, typically advanced composition would have you, typically advanced composition written such that each algorithm has the same epsilon budget. But our protocol is special in that we have the JF execution consuming only a fraction of the budget. And this fraction is determined by the neighboring input. So the inputs are very close together, then we only consume a little bit of the epsilon. And another thing to know is that we have the L2 distance between the inputs is at most 1. And our generalized advanced composition theorem says that if you consume only epsilon sub j for algorithm j, then the total consumption is just the L2 norm of the consumption vector. And that turns out to be just epsilon. Next. And the little delta just hides a log 1 of a delta term. Next. And this is a generic analysis. Any scalar sum protocol, this special consumption property works. Actually, it's not that special. You can think of Laplace as also having this property. Next. And so the open question on my mind is can we improve the communication complexity while keeping this amounts of error? currently the communication is linear in D because we're running it D times in parallel. But so can we leverage some sparsity or other structural assumptions on the data? Like, can we like somehow reduce this parallel executions to like less than D? Next. That's it. Thank you for watching and listening.
Thanks a lot, Albert. Are there any questions?
Can I just ask a, oh.
Seems like Abradip has a question, and then Suwon can go after.
Hi, Albert. Yeah, my question is very short. Why do you call it a generalized the advanced composition? Why is it generalized advanced composition?
Right. I guess like at least that's typically written in text. It's like you have the algorithm is like epsilon delta dp, and you just plug in epsilon delta to your like formula and like get the overall epsilon delta. But here we're having something like a bit more specialized. Where like it's more of a claim about the divergence. So if you have the divergence of the jth coordinate is so and so, then we plug it in. So that like it's kind of input dependent rather than like max over inputs.
I see. And does it significantly change the analysis?
Yeah, we do have to have this like per pair of inputs analysis. It doesn't work if we have like, so our scalar sum protocol does have epsilon delta for each one, but like for any pair of inputs, it only consumes a fraction of that epsilon.
I see.
So it's kind of a per input kind of analysis. So it's kind of hairy, but.
Thank you.
Yeah, sorry to be like this, Siwong, but we have to keep moving. So if you don't mind asking your question on the chat, I'm sure Albert can address it.
Fine.
And thanks so much, Albert. Let's keep going. All right, so next we have Balle from Urbana to talk about, next slide, certifiably robust federated learning in adversarial environments. Go ahead, Bo.
Okay, thank you everyone. It's a very pleasure to share the research about certifying robust federated learning in adversarial environment. I'm Balle, I'm the assistant professor from UIC. Next, please. So first off, we know that machine learning is ubiquitous in our world and it has brought a lot of convenience. But of course, we know there are a lot of security and privacy concerns currently. For example, in 2016, the Associated Press Twitter account was hacked with phishing emails and spread the rumor that White House had been attacked, and which triggers our autonomous trading bot to dump a large amount of stocks within seconds and swap a big number of $1 billion. And similarly, for privacy concerns, it has a lot as well. Next, please. Yeah, next. So basically, based on these concerns, we can see in our lab, we mainly focus on provide and certify the robust, private, and explainable machine learning paradigms. Yeah, please go through the animations in this slide. So basically, that means given a centralized machine learning model, there are different topics under it. For example, different types of adversarial attacks and certifying robustness against these types of attacks, and how to provide a quantitative model explanation, including helping the fairness and ethics, etc. And finally, different types of privacy attacks and privacy-preserving types of machine learning model and data generative models. So in this talk, I mainly focus on answering some questions here under the federated learning framework. Next, please. So you can see under the federated learning framework, considering different constraints under the edge device, etc. We mainly want to ask 3 questions. First is how to provide the strong privacy guarantees for users via the data generative framework. And second is how to provide the robust certification, which is not exist currently yet against the poisoning attack. And third is how to quantitatively measure the contribution of different participants. Next, please. Yeah, okay, next, sorry. So the first work will be the related differentially private scalable data generative models via this like data aggregation framework. So basically, the high-level idea is that we hope we can train a differentially private data generative model such that it can generate data and for flexible downstream tasks. And of course, we know this is hard because the gradient usually is of high dimension, and if we want to add noise during this data generation process, the privacy budget is easily exhausted. So the idea here is that, first of all, we can partition the data into different small partitions, which can be trained on local models, leveraging the Plate framework. But here is a data generative model, so that each data partition can be trained on the local models, and for each local user, they will clip the gradient and actually also compress their gradient and add noise and send back to the student generator, which is trained on the server side. And theoretically, this framework actually provides the first convergence analysis for these types of noisy compression gradient aggregation. And empirically, please go to the next slide. We can show that this framework actually can provide very high data utility under high-dimensional data, including some MNIST and fetch MNIST, and also later on have the evaluation of like celebrity A and place 336. So basically, it shows that the utility is high even under small epsilon budget, like epsilon smaller than 1. Yeah, next please. So based on this, and the next question is, if we can solve the privacy concerns with generative models, how we can provide strong robustness guarantees against training time attack. Next, please. So this work, led by my student Tulixie, actually provides the first certification robustness against the poisoning attack. Certification means that you can provide the lower bound of the accuracy given any training data point, as long as the perturbation satisfies certain constraints. And here the process is that during training, each agent will send model updates to the local global server, and the server will clip the model the model updates, and then add noise and send back. And very interesting, during testing time, the global server will perform the parameter smoothing and make predictions for the test instance. And next, please. So based on this framework, we can theoretically prove that such a robustness guarantee can say that with a model trained and with and without poisoning data set, it will always provide the same prediction for the same given data set. That means the poisoning attack during training will be useless under certain constraints. And here we provide the first closeness of the model aggregation in each step by viewing the process as a Markov kernel after smoothing aggregation, and then we can leverage the closeness of the models to provide a certain guarantee. Yeah, next please. So basically, here is some evaluation. The x-axis shows different radius, which means the perturbation constraints, and y the certified accuracy. So basically, we can see under different parameters, the certified accuracy can make a trade-off with different like model smoothness, etc., and can achieve non-trivial like certified robustness. Yeah, next please. And finally, I want to introduce briefly about the quantitative evaluation of the contribution of different agents. Yeah, next please. So here I will be very brief, which using the Shapley value to consider different local agents' data as a player, and the Shapley value itself is 2 to the power of n complexity computation. So here we provide the first linear algorithm like with big O n log n complexity by considering local agent closeness, and therefore we can compute the Shapley value. And next please. And for different applications, for example, do the data summarization and noisy label removal, etc. Yeah, I think that's all. Thank you, everyone. Happy to take questions.
Thanks, Bo. Any questions from the audience? I have a very quick question. I didn't get the definition of certifiable. Could you maybe repeat that?
Sure. Yeah, sure, definitely. So the certification means that given the data, say poison data D prime and the clean data D, hopefully the model trained on these two data sets, under the attack, the model will perform differently, but we want to certify with our protocol, given any test data, this two model will behave exactly the same, which means the poisoning instance will not be useful. That's a certification.
I see. Go ahead, Peter.
Yeah, I wanted to ask Bo, there's been some work that connects differential privacy to also certifiability against attacks. Can you comment on how this is different? What are the shortcomings, so on and so forth?
Yeah, thank you. That's a very good question. So there are some related work on connecting differential privacy with evasion attack robustness. So that evasion attack means testing time attack, but there is no against the training time attack yet. Actually, we have a follow-up work directly proof that the robustness is free in federated learning, because as long as in federated learning you satisfy DP, it will certify some robustness against the training time attack. So that is different from this framework, but another certification, I would say the second certification about robustness against the poison attack. And indeed, the differential privacy laid it for free. Yeah. Thank you.
Thank you.
All right, let's keep moving. Thanks a lot, Bo. Borja from DeepMind will give the next talk, which will be on reconstructing training data with informed adversaries.
Thanks, Adria. So, hi everyone. This is not necessarily like a federated learning problem. This is a general problem about releasing machine learning models and about how like reconstruction attacks can help us quantify what a privacy adversary can do when they get access to this release model. So, as you might be aware, there's a very compelling line of work by Nicholas Carlini and collaborators that they show that this kind of like reconstruction attacks, given a machine learning model, can be very successful on generative language models. But for more standard like machine learning tasks, like the prototypical image classification task, generally the focus of privacy attacks is on membership inference. And in my opinion, these membership inference attacks that are out there like are getting better and better, but they have sometimes like a couple of limitations. One of them is that there are applications where maybe membership information is already public, and actually what would constitute say privacy violation that would disappoint users is the possibility of reconstructing, not being able to infer membership. Another one is that in practice, usually to actually perform these membership inference attacks, we need access already. We already need access to the data point that we're trying to test membership of. So it's also like doesn't make sense in this application where the leakage comes from actually getting access to the data point. So what we were interested in doing in this project was to study on even one side of the leakage spectrum, we have this one bit that is the membership, and membership inference attacks look at this, like what happens on the other side of the spectrum, which is when can an attacker reconstruct like the whole of the training data points from the machine learning model. So can we go to the next slide, please? So here I'm showing you like some examples of reconstruction images on CIFAR10. So here like even columns are original data points and odd columns are reconstructions. So you will see that visually what we can extract from the model using our attacks has like a high degree of fidelity. These are not attacks against a state-of-the-art CIFAR10 model. These are attacks against like a 50K parameter model that achieves like roughly 40% accuracy, but it doesn't overfit. And the reason for this is because our attack is a bit expensive and we're working on scaling it up. But let me tell you briefly how we achieve these reconstructions. Next slide, please. So the threat model that we're using is the Informal Adversary, and there's like some references to this going back to the origins of differential privacy. Basically, the idea is that there's a model theta that is being released by some model developer. This model theta is obtained by using a training algorithm A and a training data set that is composed of a fixed part plus a distinguished data point Z. And then we assume that this model is released, is given to the adversary, who on top of this model has also knowledge of the training algorithm A, and also has knowledge of the fixed part of the data set, so doesn't know all the data set except one point. And for the missing point, they might have like some kind of prior that can be like samples or can have like some explicit probability distribution like a generative model. And if you know what a little bit about differential privacy, you'll realize that if I take a prior that is concentrated on Z and an alternative point, this is exactly the same threat model that occurs in the differential privacy definition. So under this threat model, where the adversary might have like a different prior that is more sparse than the usual, it's more diffuse than the general differential privacy one, we can perform this sort of attacks as shown in the next slide. And the way we do these attacks against neural networks is by using neural networks actually to perform the attack. So the way we perform these reconstructions is we train network phi. And this network phi is a neural network that will take as input like a flattened vector of all the parameters of the model that we're trying to attack. And we'll produce an image as output. So what we design is a training protocol for this network phi, where basically the adversary uses their knowledge of the fixed algorithm A, the fixed data set fixed, and the prior to like generate shadow versions of the model phi. We just change on one data point. We generate several of those. We use them to train the reconstructor network phi, and then we apply it to the released theta, and we obtain the reconstructions that I showed you earlier. Other things that we did in this project is like a comprehensive evaluation of these kind of reconstructions, when they are possible and when not. So if you're interested in this, we can talk more about tomorrow at the poster. We do experiments with MNIST and CIFAR-10. We look at how much information the attacker needs to collect and process to be able to generate like a good reconstructor network. We investigate what hyperparameters in the machine learning pipeline affect or don't affect the success of reconstruction, all things like the randomness in SGD, and even some extensions to just when we just have black box access to the model. On top of that, if you're interested in theory, we have like some simple results about what is feasible to do in this setting for convex models, where things are much easier. And we also have some evaluation of how differential privacy protects against reconstruction attacks and which epsilons are needed to be able to protect against reconstruction. Thank you.
Thanks, Borja. Looks like Emiliano has a question.
Really interesting work, Borja. I was just wondering, quick question. I don't know if I missed it. Do you have a paper somewhere online or that you can share?
Yeah, there's a paper that is accepted at the Privacy and Machine Learning Workshop at NeurIPS. I think should be easy to find an open review if you search for the title. And we'll put a more extensive version on Archive in a couple of weeks. Yeah.
Okay, I searched, but I didn't find it. But maybe I put the wrong. Maybe I was using Bing. Yeah.
Should show up.
Aurelian also has a question, which was partly answered already. He said, adversary knowing all data except one point already implies having an arguably quite good prior on data distribution, no? That's on the chat, Borja.
Yes, sure. You can. Yeah, I mean, this is how we construct the prior in practice. We use other. We use data points from the same distribution, but we use them. We use data points that are actually disjoint from the points that are used to train the model, just to make sure that there's no cross leakage. One thing that we've also managed to do is to use points from another distribution. So, for example, we can now train the attacks against CIFAR-10 using psi knowledge that comes from CIFAR-100, which is disjoint from CIFAR-10. So yeah, maybe they're the same distributions to some extent, but you can do this with other data sets as well.
Nice. Brendan?
Yeah, when you say that the adversary knows the algorithm A, does that include like the random initialization of the network and exactly what order the fixed part of the training data is processed in?
Yeah, that's a very good question. We have experiments on both settings. So we've decoupled the two sources of randomness in SGD. One is the random initialization, and the other is the subsampling in the mini-batching. So our experiments so far show that if you don't know the initialization, things become quite tricky. And we have some illustration on membership inference attacks that fail even in this threat model. So we think that this is kind of intrinsic. But there's also like a lot of settings in which maybe it's reasonable to assume that you have the initialization, like either the code that the adversary used comes with a fixed random seed, or the model developer used comes with a fixed random seed, or actually like the model that is being released is a fine-tuned version of a public model. And for the randomness in subsampling, we show that knowing the seed helps, but if the batch size is large enough, you can also do pretty good reconstructions even without knowing the seed on that front.
Thanks.
Cool.
Thanks a lot,
you.
Borja, and everyone asking questions. We should
Thanks.
keep moving now. Next speaker is Amir from UMass, and he'll be speaking about the critical evaluation of poisoning attacks on federated learning. Go ahead, Amir.
All right. Hi, everyone. This is the work led by my student Virat and integration with Peter and Dan from Google. Next, please. So perhaps one of the key reasons federated learning is becoming so popular is that it doesn't need to make any strong trust assumptions between the participants in federated learning to perform collaborative learning. Next, please. This can also become its Achilles heel because, next, please, because some malicious adversary could try to, who controls some of these participants, could try to corrupt the global model by sending malicious updates during the training process. Next slide, please. So the ultimate goal of this study is to understand the significance and importance of poisoning attacks on production FL systems. So the FL systems that are going to be used and are being deployed in production systems. Next, please. So there's three variants of poisoning attacks when it comes to federated learning. Next, the first type is, and the red line box is a little bit misaligned, but assume it's untargeted. The first class are targeted attacks where the goal of adversary is to impact the accuracy of the model on a select set of input samples or input sample class. Next. The second category are backdoor attacks, in which case the goal of the adversary is to impact the accuracy and the confidence of the model on select input classes which contain some trigger, either semantic or artificial. Next. And finally, the third class are untargeted attacks, in which the goal of the adversary is to impact the accuracy of the global model on arbitrary input samples. Next, please. So the first question we ask is, which of these three classes of poisoning are in fact more critical and important to production FL deployments? And the answer to this question could be contentious, but next, please, would like to argue that it's the untargeted class of poisoning which is the most important class to production FL systems. Next, please. So the first reason is that untargeted poisoning has the potential to impact many more participants compared to the other two types of targeted and backdoors. So in fact, in the targeted and backdoor by design, they're going to impact a small fraction of sample like inputs from the samples from the input space, and many of them in fact could be artificial samples which may not be observed by actual users. Whereas in the case of untargeted poisoning, the goal is to impact any input sample and kind of reduce the accuracy for arbitrary users. Next, please. So targeted and backdoor attacks by design introduce a disparity of performance between the target samples and the rest of the samples. And therefore, this could be used to detect the use of targeted or backdoor attacks. On the other hand, in the case of untargeted attacks, these are designed to equally impact all input samples, and therefore, in practice, they could be undetected for a much longer time. So they could be, your model could be poisoned with untargeted poisoning for a very long time without being detected. Next, please. And it's worth mentioning that designing untargeted attacks is technically more challenging, because now your optimization goal is to impact not just a few samples within the training space or within the sample space, but arbitrary input samples. Next, please. So we narrow down our focus to understand the impact of untargeted poisoning attacks on production FL systems. Next. So this is an overview of what we've done so far. We try to develop a systemization of knowledge for untargeted FL poisoning. Next, please. We try to enumerate all threat models that pertain to FL poisoning and try to identify the threat models that are more relevant to practical deployments of FL in production systems. Next, please. We try to comprehensively overview existing defenses proposed for poisoning attacks and try to identify those that could be in fact used in practice given constraints of practical production systems. Next. And finally, we try to do comprehensive experiments on a selected set of attacks and defenses from the literature to understand the status quo of poisoning attacks on production systems. Next, please. So I'm going to summarize with three main insights from our work. The first one is that the threat models and set of parameters used in the literature seem to deviate from what we expect to be realistic for production systems. And therefore, we argue that perhaps some of the conclusions made by these works in the literature might be questionable and debatable. Next, please. Using the right set of parameters and threat models, we show that at least the state-of-the-art attacks are not quite impactful when it comes to production FL systems. And we see that they're not making the impact that would be important for a poisoning attack. Next, please. Even though there exist different countermeasures and defenses against poisoning, some of them are complicated and advanced. We show that for the threat models and set of parameters that we see practical for production FL systems, in fact, the simplest countermeasure could be enough. So like, for instance, to defeat data poisoning attacks, we show that it's enough to just put a limit on the size of data set contributed from every client. And similarly for like model poisoning, we show that the simple norm bounding could be enough to kind of prevent the attack under threat models for production systems. Next, please. That's all. We have a tech report for further discussions and analysis, and I think we have a poster tomorrow or today. Thank you.
All right. We have just one question, but Suhas, sorry about that, Brendan, but we are tight on the schedule.
Yeah, but just a quick question. That is, well, how are you defining a production level system? This seems a bit vague in my understanding.
Yeah, that's a very great question. We don't know. No. So, in fact, so this is a lot of kind of details on how we formulate is based on last year's FL workshop from Google. That there were some breakout sessions of like experts like all of you guys discussing the set of parameters and threat models that people assume for practical systems. So a lot of those, I think, so like in the paper, we offer a range of parameters and also some discussions on potential threat models for production systems. But again, it's based on, I mean, someone has to define it, and we're relying on the discussions from last year and also some private discussions with other experts in FL.
Thanks so much. Thanks, Amir. Moving on, Hamed from Imperial will give the next talk, which is titled PPFL Privacy Preserving Federated Learning with Trusted Execution Environments. Off you go, Hamed. Nice to see
Thanks very much, and nice to see all good friends here. I'm Haddadi. I'll briefly talk about this work, which this happened this year. So it's mostly a systems work where the client and some people that we were working on, they needed an end-to-end deployable system, but with specific privacy constraints. So what we did, we worked on this work, and this got published in Mobisys this year, and it actually got the Best Paper Award in Mobisys. So if you go to next slide, so the idea was that how can we provide the basic privacy defenses for federated learning and have basically a fully private and kind of leakage resistant system, but without losing too much in terms of utility side and also not at a massive overhead in terms of computation. So what we went ahead and built was an end-to-end system where we started the training from deep inside the client's TE, and basically there's a kind of a greedy layer-wise training, and kind of the layers of a model move in a kind of a train manner in and out of the TE, and the training happens inside the TE. But the important thing is that also on the server side, there is an SGX, so an attestable server is doing the secure aggregation, and you have a TLS connection ending at both sides. So you have on the client side and the server side the TLS connection ending end-to-end, meaning that the server could only do aggregations as it's available on its trusted execution environment. So it's attestable to the clients, and also the clients cannot necessarily, for example, see deep inside the models, for example, or you can basically protect specific layers. So in terms of the overhead on client side, these are the numbers there. So we have about 20% overhead on a handset. So you can think that this is not something that you would be running daytime on somebody's phone, because 20% of somebody's phone battery is not nice, but it could be a classic overnight sort of thing. So if we go to the next slide. So the idea is that you have a model and you have a heterogeneous environment. You have loads of millions and millions of users with different, for example, handset types. So what you can do is that you can, in a way, you can select the model that is suitable to the types and classes of the clients that you have, and you ship these models as your global models. And so this acts as your initial kind of seed model. And then the client, when it receives this model, they train either layer by layer or blocks of layer where their TE is available. So you usually, in terms of, for example, trust zone, you're talking about kilobytes of memory available in today's, for example, devices. But you can shift layers in and out, and more importantly, for example, depending on the type of attacks that you have. So here we are mostly looking at the classic attacks in federated learning that a lot of your works have covered. So membership inference attacks on the client and server side, the property inference attacks, and also data reconstruction attacks at the server. But at each stage, when that layer, when you use this greedy local training and that layer converges, you send the updates back up over the TLS channel to the SGX, so where the secure aggregation can happen. And you keep repeating. And the interesting thing is that now you don't also have a uniform clock for the whole population, because in some clients you might be able to actually run more layers in the TE. So you might actually reduce communication from what we saw based on the data that we have. So if we go to the next slide. So the setup that we have and the system that we released, it uses the Opti on the client side. So using an ARM high keyboard, which is a 4 Cortex ARM device. And for the server side, we use the generic SGX machine, which in this case was an Intel SGX with a server and a TLS and hard-coded session keys inside the both client side and server side. And you had the end-to-end pipeline. And we used very standard classic data sets and models, VGG19, MobileNet, and MNIST and CIFAR and all of that. So we tested across all of these for the standard attacks. So we were looking at basically where you could, for example, prevent, and you can achieve nearly still perfect model utility in terms of training. And one thing that you can do, for example, you can prevent against membership inference attacks by actually keeping the last layer inside the TE and never transmitting it back. So this was kind of quite interesting for us as well, that you would still get quite good accuracy. And so if we go to the next slide. So we saw that the actual, across the different models, somehow the quality of the slides, even for me, is very low here. I don't know if it's the same for you. But the idea is this. The idea is that the overhead in terms of CPU time on the client side was not more than 15% or so. Memory occupancy had about 20% extra overhead in terms of back and forth across the TE and the rich execution environment, RE, and about 20% increase in energy. And we used the standard FedMA and Fed average algorithms, and we achieved relatively good results. And thanks for the reminder, Adria. But in fact, this is it, and I can stop here, and happy to take any questions. The full framework and code is available for this online as well. Thanks very much.
Looks like Emiliano has a question. Go ahead.
Yes, please.
So, quick question. I remember seeing the paper a while ago, and there was one sentence in the paper saying attacks, side channel attacks, are out of the scope of this paper, which is fair because you did not publish it in security venue. But can you comment on? I don't really know much about trusted TEEs and attacks, but I was just wondering if you could comment on that.
Yeah, so for example, you have side channel attacks on SGX if somebody has nearly physical access to the device. So there is that risk, and there is patches against that, and there's been back and forth in the security community. But I think that's something that is a shortcoming of, for example, today's SGX environment. For example, the ARM Nitro enclave does not have that issue. So I think, there will always be some sort of attacks on secure memory, and this is not going to stop today. But I think this was a nice. Our technique will work anyway. It's just that now it's up to hardware manufacturers to make their belt tighter, which is
So I have a somewhat follow-up question. I was going to ask why SGX, but now I'm going to ask why would you use ARM Nitro if you had to write?
Yeah. Of course, at the time, ARM Nitro wasn't as easily available as it is now. So at the moment, our installation is actually on Nitro for the actual use case. But yeah.
Is that because of security or usability?
Usability. Number one, also SGX at the time needed the Intel attestation service to run for like a commercial setting. So you rely on Intel, but with Nitro, you don't have that third-party kind of interaction and overhead. Although SGX is also changing, but so is also TrustZone. I cannot say much more than this, but TrustZone will be also changing massively in the next 2 years. So yeah.
All right. Thanks, Hamid. And
thank you very much.
Let's move on to the next speaker.
Thanks for having me.
So next speaker will be Suhas from UCLA, speaking about privacy performance trade-offs in the shuffle model of federated learning.
Hello. Okay, this is joint work with my PhD student Antonius Girdis, my postdoc Dipesh Datta, and two Googlers, Peter Karus and Tirtha Suresh, who are collaborators in work that we've been doing over the past year or so. Next slide, please. So, of course, in a federated learning workshop, we don't need to put up the slide, but I just wanted to sort of put up the trust model, which sometimes gets diffuse. And so the trust model here is that we do not trust the server, and therefore we want to give local privacy guarantees, and we want to try to see how we can do that. So next slide, please. So there are considerations other than just privacy, of course. The consideration could be also communication efficiency, and we've been thinking about that as well, and where we can get significant compression along with privacy and performance trade-offs, and also subsampling, which I will talk about a bit later in the presentation today. Next slide, please. So just to set this up, in central differential privacy, as most people here know, you have a sort of a trusted curator, and the adversary is a data analyst who accesses information from that trusted curator. And it's not necessarily appropriate for distributed setups. And next slide, please. So the right potential framework for this is in local differential privacy, which has been studied for decades. And the idea is that each user randomizes and the guarantees are given against the untrusted analyst. And so this is sort of when you take in the 60s, this was done in randomized response through surveys, private surveys, and so on. Next slide, please. So the advantages and disadvantages are the following. When you do local differential privacy, you don't trust anybody. When you do central privacy, as you said, we trust the curator. When you take into account error, because you don't trust anybody in the local differential privacy framework, you are getting poorer performance, and in central DP you could get less. And can we achieve the best of both worlds? Next slide, please. So this is related to the talk that Albert also gave about shuffling, and this is work that has been done for the last 3 or 4 years, which is a very powerful line of work on using anonymization and therefore shuffling for privacy. And the idea is to take a effectively present a random permutation to the untrusted analyst. And this can be done potentially through anonymization or many other mechanisms. But if for the purposes of this talk, we assume that there is a trusted shuffler which interfaces between the users and the untrusted analysts. Next slide, please. So the other aspect that we will focus on a little bit today is on composition. So whenever we talk about learning models over many iterations, you need to give compositional guarantees. And the standard compositional guarantees using advanced composition theorems could be improved upon. And this was done in work by Haddadi et al., which was presented in CCS a few years ago, and put into the framework of Rene differential privacy by Mironov later. And so we will use this framework, which enables us to give strong compositional guarantees for our work. Next slide, please. So the basic idea, which is work that will be presented in CCS this year, was essentially to try to understand the Rene differential privacy, which is essentially enables us to give stronger compositional guarantees for the shuffled model. And we did this for discrete mechanisms because we actually also could incorporate compression into this. And we had both upper and lower bounds. These expressions might look a bit ugly, but in a sense, it gives some insight into how the shuffling can help and how this composition can help. And we have both a gap between the lower and upper bound, which we are hoping to close fairly soon. So next slide, please. So there is the technical challenge in doing this is that analyzing the Rene differential privacy directly for arbitrary data sets, neighboring data sets, is non-trivial. And what we do is to show that this can be actually connected to analyzing the RDP for special neighboring sets, which have all the same components except the last component being different. And once we make that connection, we are able to do our RDP analysis for these special data sets, enabling us to prove this result. Next slide, please. So given all the work, one of the questions one would ask is, what is the advantage of doing this? And one can show that we can get significant advantage, or a factor of 8 or more, over the state of the art when we publish this work, when we do over strong composition. And essentially, this enables a stronger result in terms of privacy. Next slide, please. And we applied this also to the optimization framework, where we allow for sampling, so in particular client sampling. So the challenge is that you can actually use client sampling, which many times naturally occurs in federated learning, to enable amplification. But how to analyze this is, along with the Rene differential privacy, was the technical challenge. Next slide, please. And we were able to do this. This is work that is going to be published in Europe. And we showed that it can beat the state of the art, and actually sampling can also significantly help in giving privacy guarantees. And that once we put it together with the optimization framework, we can show convergence bounds for with compression and therefore the learning performance. Next slide, please. And this is just to put up the results. We'll be happy to discuss offline, or we can look at the paper. Next slide, please, to show the numerics. So essentially, through this mechanism, you can actually get significant improvements with sampling. So if you now naively incorporate sampling into our earlier framework, we actually can significantly improve over that as well. And if you use the more traditional composition plus sampling mechanisms, we can get an order of magnitude or more improvement in privacy. Next slide, please. And the final slide is essentially to show that with this framework, we can actually, the top part of the figure, apologize, is cut off, but essentially running it on MNIST data sets, and we can show that you can get a significant improvement either in terms of, for a given privacy parameter, the accuracy improvement, or for a given accuracy, the privacy parameter improvement. And so I will stop here. I'll be happy to take any questions or comments.
Thanks a lot, Suhas. Are there any questions? I have a very, very quick one. I missed a comparison with the central model. I see this comparison with clones.
Yeah, so our comparisons. So the comparisons that we were making were all with the distributed models.
I see.
But what we showed in the optimization framework is that you can actually that's a theory result in terms of convergence rates to the compared to the centralized models.
Thanks a lot.
Yeah.
Thanks a lot, Suhas. So let's go for the last talk of the session by Phillipp Schopmann from Google on distributed point functions.
Hi, yeah. So I'm going to talk about distributed point functions. I'm not sure, is that my slide? It looked differently. But yeah, so this is work coming out of the private computing team at Google. And it's going to be about efficient, secure aggregation via non-colluding servers. So next slide, please. Let's talk a little bit about the background on secure aggregation. So we have a setting where we have lots of clients. So think millions of clients, here depicted by Chrome browsers. And in the center, we have a single server, and we want the server to learn the aggregation or the sum of all the client's contributions. And these contributions, usually they are vectors. So we need some kind of protocol that is performed between the clients and the server that allows the server to learn the sum of the contributions, but not anything else. So in a special case, next slide, please. In a special case of this secure aggregation setting, the clients have only one hot contributions. So that means the vectors that the clients contribute have a single non-zero value, and all the other values are zero. So then the sum of these vectors can be seen as a histogram at the server side. And if the domain is very large, so if the dimension of these vectors is large, then this will be a very sparse histogram. Now, with the existing single server aggregation protocols, this gives us some problems. So for one, we need an interactive protocol between the clients and the server. And that means, in particular, if we aggregate many and large values, that increases the chance of dropouts and with all the problems that entails. But the second much bigger issue is that the communication, so the size of these encrypted ciphertexts of one hot vectors, usually needs to be as large as the domain size in the single server setting again. So that means we need a lot of communication from the clients. And now one way to get around these limitations is, instead of using a single server, we use two servers, so two aggregation servers. And the goal is for each of them to learn an additive secret share of the resulting histogram. And now, as long as these two servers don't collude in the process, and only in the end aggregate the final histogram, then this protocol is secure. And so this assumption of non-collusion, we can try to enforce it, for example, by putting the two servers in different organizations, in different jurisdictions, and so on. So in this setting, the clients generate secret shares of their inputs and send one of these shares to each of the servers. And now the servers can locally aggregate or expand and then aggregate the secret shares sent from the clients, which gives them an additive share of the entire histogram. And only then they aggregate the entire histogram, and we get in a central location the result. So the advantage of this approach is that we can have unidirectional communication. So from the client's perspective, it's just you send a message and you're gone. So there's no complicated protocol needed. And the second one is that there are secret sharing schemes, specifically functional secret sharing, which I'm going to introduce next, which allow us to have messages that are only logarithmic in the domain size. So this is very useful if we have these large domains with one-hot vectors. And finally, there are verifiability schemes, so verification schemes for these settings. So in fact, it's possible for the two servers to verify that a client's message has a certain structure or has a certain value in a certain range and so on. So next slide, please. Yeah, so here you see this in the picture again. The clients each send a message to each of the servers. Each of them have a size of only log d. The servers locally aggregate, and then each of the histogram values will be a secret sharing between one share held by one server and the other share held by the other server. So next slide, please. Now I'm going to talk quickly about the exact secret sharing scheme that we're using, and that is called a distributed point function. So as I said, we want to aggregate one-hot vectors. And that means we have a single non-zero value at a single location. So this is here depicted as alpha and beta, where alpha is the index and beta is the value at alpha. Now what the distributed point function allows you is to split up this function that has value beta at index alpha into two key shares and distribute them to the servers. Next, please. So the servers can now locally take these small keys, expand them to long vectors. Next, please. And then only if you add up these long vectors, you get back your histogram. So what's nice about distributed point functions is that they come in an incremental flavor as well. And that allows you to not only evaluate the entire domain at once, but it allows you to evaluate a prefix of the domain. And that makes, that allows you to scale to really large domains. So next slide, please. With these incremental DPFs, what we have instead of a single index alpha, we have a series of indices, alpha 1, alpha 2, and so on, that each are prefixes of each other. And similarly, we have one value beta with each of these prefixes. So the client, again, can secret share this now prefix DPF into key shares. And the servers now first start by expanding on the first prefix, which is alpha 1. Next, please. So that means they get a much smaller histogram, but in this much smaller histogram, they can already identify which values will be non-zero. So under which prefixes there will be not a single non-zero values among any of the clients. So that means we only need to recurse, or we not only need to continue the expansion under the buckets that actually have non-zero values. And next slide, please. That is done iteratively through each of these prefixes until we get to the final histogram. And in this process, the servers don't need to perform computation proportional to the entire domain size, but only proportional to the actual number of non-zeros. So that means we can scale this actually to really large domain sizes, such as 2 to the 32 and something like that. So next slide, please. We have an implementation of these distributed point functions, and that is open source on GitHub, so please feel free to check that out. And the goal was to have flexibility and high performance at the same time. So we want to perform these hierarchical queries, and we also want to be able to aggregate all types of vectors. So not only on single integers, but for example, XOR shares of bits, or prime field elements, or tuples of values, and so on. So all of this is supported in this library, and we're looking for users and contributors. So if you're interested in that, please reach out. Thanks.
Thanks so much, Philip. Unfortunately, we don't have time for questions. We're running late. So let me thank everyone for the fantastic talks and all the questions. And it was really great. I enjoyed it a lot.